I welcome you back to this lectures of railway engineering. Today we are going to start with sleepers, and in this lecture we may be giving a focus to density and the spacing. In the previous lecture we talked about the flat footed rails. We discussed about the different rail lengths which are available and how they are color coded so as to identify them. The tolerances with respect to the vertical and horizontal direction at different locations of a rail section, the various types of the tests which are conducted on the rails, which are dependent on the grade of the steel which is being used in a manufacture of rail. And we did talk about the flaw detection and the rail failures and the nomenclature of a failure. Today we are going to start with sleepers. The very first thing which we will be discussing is about the functions, and then what are the requirements which should be there. Then we will move to the sleeper density, and finally to the sleeper spacing in different environments of the track. Let us start with the sleepers. So, what are sleepers? As you can see in the photograph on the right hand side, we have the rails, and these rails are being supported by some item at the bottom of it, and these are basically the sleepers. So, the sleepers provide support to the rails so that the load can be transferred efficiently to the lower layers or support systems. So, whatever the load is coming to this rail is going to be transferred to the sleeper, and half of the sleeper we assume that it is coming into that influence, and it will transfer the load to the ballast below. Now, these sleepers, they have to be embedded in the ballast cushion, and once they have been embedded, it has been packed there, then they will remain in position. They will not start moving this way or the other way. So, that is also an important aspect, and this sleeper along with the ballast together is going to give some strength to the track. The another thing is the rails are connected to the sleepers using different types of fastenings which are suitable for a type of sleeper. In the old days, you must have seen the wooden sleepers have been used on the railway tracks. Slowly and slowly, those wooden sleepers, they were changed to cast iron or steel trough sleepers. And then finally, nowadays we are using the concrete sleepers. And again, in the concrete sleepers, there can be different varieties, different types and designs. So, based on that, we need to see that what type of fastenings can be used and what are going to be suitable so that their sleeper and the rail, they remain intact in position. So, what are the functions? The functions are, it should hold the rail to the correct gauge and alignment. So, whatever the alignment is there, if we talk of alignment here, so this is the alignment of this particular track, whereas the alignment of the track on the left hand side is going towards the left, it is taking a turn. So, whatever is the alignment being given or the profile being given of the track, that should be maintained, and the rails should remain in that correct gauge position. If you are talking about a broad gauge, so 1676 mm shall remain there. It should act as a tool to rectify the track geometry. We can use these particular sleepers to do that also. They shall provide a firm and even support. So, design has to be such that the rail gets seated at the top of the sleeper in a easier manner, and then that support which is there is not something like at the top irregular, it has to be a even support on which we are putting the rail. They shall act as an elastic medium. They should be able to absorb blows and vibrations which are going to be induced in the tracks because of the higher speeds, because of the clearances which are available in the track with respect to the wheel and axle arrangement and the lateral movement of those wheels and axles because of either the track geometry or the alignment or because of any irregularity in the track or the forces which are acting in the lateral direction. It should provide the longitudinal and lateral stability to the track. So, in combination with the ballasted system, obviously this is going to provide that sort of a stability, and it should transfer the load from rails to the wider area of the ballast, which is provided as a cushion below the sleepers. So, these are the functions which are there, and on the basis of these functions we can very easily derive the requirements. So, if we have understood all of these functions, that is not a problem. So, what are the requirements in that sense? The very first thing is they should be easy for maintenance and they should be easy in gauge adjustment. So, whatever sleeper has been provided at the bottom and a rail has been placed at top of it, there should be a possibility of adjusting the gauge if it is going beyond the tolerance limits. Fixing and removing of fastenings should also be easy. So, fastenings here we are talking between the sleepers and the rails. These sleepers should not be very heavy, but at the same time they should not be less in weight. So, there should be a moderate weight, and this moderate weight also has to be looked in a sense that they should be easy to handle. It should not be a requirement that we need very heavy machinery to bring at the location where the construction or the renewal is going on, and then so as to lift the sleepers we need to do that. Sufficient bearing area. So, the design. So, this basically talks of the design. Design in the sense that what is the shape of that sleeper which is being provided. And when we say shape, the bearing area is going to be at base. So, if you are talking about something like this, a trapezoidal section which is there in the case of concrete sleepers. So, this base is the bearing area. So, we are interested to look at that. It should be able to absorb the shocks and vibrations. So, it should not happen if the shocks and vibrations comes on the rail which is being placed at the top of it, then in that case the deterioration or the damages starts appearing in this because of that. Track circuiting must be possible. It should not create a problem to the track circuiting. So, the material of that sleeper has to be in that form. It should be anti-sabotage and anti-theft quality. It should not happen that we have provided a sleeper and the next day when we come there we found the sleepers are not there. So, they have to be designed in such a manner that once they have been fixed and they have been jointed with the rails at the top, it becomes difficult to take them out and take them away. So, that is also important. Then another aspect is the cost. At what cost these have been manufactured, and then what is the maintenance cost throughout their service life. So, this should also be minimal. Another thing is the sleepers should be fit for use in the long welded rail sections or the continuously welded rail sections. And in that particular direction, what are the requirements? The requirements are that they shall have heavy weight to lend stability to packing to the track. The fastening shall have adequate continuous toe load, and there shall be long retentivity to packing so as to avoid the frequent attention to the track. Other things are it should be possible to maintain the track with modern methods. Nowadays we are using various machines. There can be like a shovel packing or on track tamping machine can be there. So, it should not happen that when those machines are working, either we have to remove the sleepers or if the sleepers have been placed in position they get damaged. That should not be the case. They shall have long life span. When we say long life span, now there are different things which have been used. We have a sleeper, at the top of sleepers we are using a rail, and the rail and the sleeper they have been connected together by use of fastenings. So, in this particular case, when we are talking about all of these three elements, they should have equivalence of the life. If the equivalence of the life is not there, then there will be periodical maintenance of one or the other item, and again the things have to be taken out, and it will create problem in terms of the operation of trains on that particular track. These shall be easy to manufacture, transport and then lay at a location. So, this is also an important case. Now, damages on the derailment shall not be excessive. So, the way they have been designed, the type of material which has been used, the type of strength which has been given. So, all of the things will come there. So, the strength, the design, the material. So, this becomes a part of the consideration, so that we sleepers remains there and they provide their functional value. Now, let us come to the sleeper density. Now, what is sleeper density? Sleeper density is expressed as the number of sleepers per kilometer of track. So, in 1 kilometer, if you see here, if this is the total track being provided, the rails are being provided, and below the rails there are number of sleepers are going to be placed. So, there can be one sleeper here, then other, then third, then fourth, then fifth, and there will be some spacing between the sleepers. So, how many sleepers are going to be there in 1 kilometer length? So, that is what we are talking here. It is fixed considering the maximum permissible speed as well as the traffic density of the section. These are the two governing factors. If the traffic density is high or the permissible speeds are higher, then we should go for a higher sleeper density, means the more number of sleepers in 1 kilometer length. How it is being expressed? It is expressed as m plus x. And what is m here? M is the length of the rail in meters, and x is a number which varies between 4 and 7. So, if we are talking about a rail which is having a length of 12 meters and say x is being taken as 4, that means what? It is 12 plus 4 is equals to 16. That means there are 16 sleepers per rail length of 12 meters. So, that is how this will come out. Now, value of x is fixed based on two of the factors we already talked about. What is the load which is coming? So, the axial load will be there. This axial load will come, will have the locomotives. There are different type of wheel axle combinations, and there will be load which will coming through those axles. The permissible speed, the type of the rail section which we are using at the bottom, because the axial load and the type of the rail section, they are correlated. We talked about formula that 560 multiplied by the sectional weight, and that is the axial load which a rail can bear. So, they are correlated in that form. Type of the sleeper and its strength. There are a number of types of sleepers are there, but nowadays, as I said, we are using the concrete sleepers, and within the concrete sleepers it can be pre-stressed concrete, post-tension concrete, or it can be any other form. So, there again the strength parameters will be different. Type of the ballast and the thickness of the ballast cushion which is being provided below the sleepers, that will also govern that what should be the value of x. And finally, at the bottommost level, the formation is being provided. What is the nature of that formation? It is yielding formation, or it is a formation which can take up the loads very easily. Then that will also define whether we need to provide more sleepers or we need to provide less number of sleepers respectively. Now, sleeper density is now indicated as number of sleepers per kilometer length of track. Previously, what we said that when we are talking about m plus 4 to m plus 7, that will give you a value for a one rail length. If the rail length is 25 meters, it will come accordingly. If the rail length is 12 meters, it will come in that form. But the universal practice across the world is talking the number of sleepers per kilometer length of the track. So, that means this value is going to be much more than as compared to say in the previous case when we said it is m plus 4 12 plus 4 16. So, that will not be the case. Now, this sleeper density per kilometer becomes relevant as the rails are used now in the longer lengths, and we are talking about the short welded rails, we are talking about the long welded rails, and we are talking about the continuously welded rails. So, when we are discussing about these type of rails, we are implementing these type of rails, then talking in terms of a one single rail length and the number of sleepers to be provided for that only one single rail length is not a justified manner of indicating these values. And the values which are used on the Indian Railways are like 1660 sleepers per kilometer, 1540 sleepers per kilometer, 1310 sleepers per kilometer. If the loads are very high, obviously we are going for this one. If the loads are quite low, then we can go to these values. Now, the minimum sleeper density is also being defined in the case of all track renewals where the complete track is being renewed and through sleeper renewals are also there, or a doubling or the gauge conversion or the new line construction. In all of these cases, the sleeper density which is to be considered is 1660 sleepers per kilometer. In the case of loop lines and sidings with a permissible speed of up to 50 kilometers per hour, we can use a lower value of 1540 per kilometer. But in the case of sidings with permissible speed more than 50 km per hour, we should again increase the sleeper density to 1660 per kilometer length. Then in the case of long welded rail tracks, the minimum value which needs to be provided is 1540 per kilometer, but in the case of short welded rail tracks, it can be a lower value of 1310 per kilometer. So, this 1310 per kilometer is a value which is used quite less nowadays, because now we are working with more welded tracks in terms of LWR and CWR, and that is where 1540 or the another value of 1660 per kilometer can be used. Now, in the case of running lines and bridging lines in yard other than the loop lines, we use this factor of m plus 4, but for other yard lines it can be m plus 2. So, it means it is further being reduced, the number of sleepers are going to be reduced. For symmetrical splits where speeds on the main and the loop lines will be the same, the sleeper density on the loop line should be equal to the sleeper density on the main line. So, what is that? It is talking about a symmetrical split. So, symmetrical split is that a track is coming in this form and then it gets splitted here as well as here. So, there is a symmetrical split with respect to this center line of the tracks. So, in these particular cases what it says, and that if the speeds are equal, then the sleeper density is also going to be same, even if this is a main line and this is a branch line, that will remain the same. Now, let us look at one numerical here. The data which is being given is the length of the rail is 13 meters and is used on the broad gauge track on Indian Railways. The track carries heavy axle loads at a high permissible speed. Calculate the sleeper density for this track. Now, in this case, the condition is being given, the heavy axle loads are there and high permissible speeds are there. That means, if you are talking about that factor m plus x, where x ranges from 4 to 7, we should go for a higher value of 7. And that is what it says. For a track carrying heavy axle loads and high permissible speeds, it is better to fix sleeper density as m plus 7, and the length of the rail is being given as 13 meters. That means m is 13 meters and x is being taken as 7. So, 13 plus 7 is equals to 20. That means 20 sleepers per rail length are going to be provided in this case. So, that is a very simple numerical, very simple case, and you have to simply take a judicious decision with respect to the information which is given to you in the numerical, and you can arrive at the value. Let us look at another such a numerical. The length of the rail here is 25 meter, again being used on a broad gauge track. The sleeper density on track is reported as 1540 sleepers per kilometer. So, sleeper density is already being given to you. What we have to look at is that what is the expression of the sleeper density for this track. So, state the expression of sleeper density. Now, sleeper density expression is m plus x, and number of rails in a kilometer length will be how much? It is a 25-meter long length of the rail. So, 1 kilometer means there are going to be 40 such rails. So, number of sleepers per rail length, we have been given the value as 1540 sleepers which are there in 1 kilometer. So, for one particular rail, then it comes out to be roughly around 39. So, 1540 divided by 40. Now, once we have this 39, so 39 is nothing but it is m plus x. So, if this is 39, so m plus x is being there and m is 25. So, what happens is, so this is 25 plus x is equals to 39 and x is going to be 39 minus 25. So, it is 14. So, the expression becomes m plus 14 here in this case. So, this is one just example that how in another case where the sleeper density is being given to you, you can compute the expression. Now, let us look at another example here. The length of the rail is being given as 12 meter. Again, it is being used in broad gauge of Indian Railways. The sleeper density is being taken as m plus 6. We need to calculate the sleeper density per kilometer. So, sleeper density is expressed as 1 m plus x, the number of sleepers per rail length. So, if we are going as m plus 6 is x is being given as 6 and length is being given as 12. So, 12 plus 6 means 18 are the sleepers which will be there in one rail length. So, the number of rails per kilometer is how many, because you are using 12 meter long rail. So, in 1 kilometer we are having around 84 rail sections like this, and then the sleeper density per kilometer is going to be how much? The sleeper density is going to be 1512. So, we have taken the number of rails and in per particular rail how many sleepers are there. So, that is how we have calculated the value. Now, let us talk about the another case of sleeper spacing. Now, two rail sections have been shown and these are the sleepers which are being placed at the bottom of the rails. This is the joint. So, the two sleepers which have been provided here, they are defined as joint sleeper. And then the next one, after that joint sleeper, it is first shoulder sleeper, then there is a second shoulder sleeper, and then rest of the sleepers they become the intermediate sleepers. In that sense, at the joint, whatever the two sleepers are there, so the spacing can be A. In another case, when you talk about the first shoulder sleeper and the second shoulder sleeper, or the joint sleeper and the first shoulder sleeper, then the spacing can be B. For first and second shoulder, C, and then second shoulder and intermediate sleepers, then it can be D. And then this D will be followed uniformly then further in the length. So, this is the overall way in which the sleeper spacings are provided, and that is what we are going to see that how these are being done. So, in the case of bridges, the maximum center to center sleeper spacing at all locations is taken as 600 mm or 60 centimeters. Increase the spacing suitably depending upon the top flange width of the cross girder at cross girder in open web girders. The clear distance between joint sleepers should not be more than 200 mm. So, at the joint the spacings are lesser, but as you are going away then you are getting the higher values. In the case of turn in curves, the maximum center to center spacing is 650 mm. The sleeper spacing shall be kept uniform if concrete sleepers are laid in unavoidable circumstances or in the case of short welded rail tracks. Then if the SEJ is being provided, that is a switch expansion gap is being provided and it has a pair of tongue rail and a stock rail which rest on 6 sleepers which are 600 mm wide. Then center to center spacing between the middle two sleepers is taken as 700 mm, and for rest of the sleepers it is either 650 or 600 mm based on the sleeper density. In the case of main lines of the normal tracks, where the sleeper density is being taken as 1660 per kilometer, the center to center spacing is taken as 600 mm. So, you can see that the situations whatever are there, on the basis of that Either we are using 600 mm, 650 mm, 700 mm, or there can be few more values as we will see when we move forward. In the case of main line or normal track with sleeper density of 1540, then this is increased as to 650 mm. Obviously, if you increase the spacing, the number of sleepers below the rail length are going to be decreased. On a LWR track with sleeper density of 1660 per kilometer, in that case it is 600. If a LWR track with a sleeper density of 1540, it is 650. That is the value we already discussed. Similarly, in the case of SWR track with a sleeper density of 1540, it is 660, now a bit different than 650. And if the density is lower, it is only 1310 per kilometer, then the value can increase to 780 mm. So, a further increase has been shown there. In the case of 1 in 12 fan shaped turnouts, which are the modern turnouts which are being used now when the track is going straight and you are going towards one side, then in this case the values have been given that at joint it is 150 mm, but then between the first and the second sleeper it is 457, that it increases to 510, then 695, then again it reduces and then it again increases, and then after that it becomes changes to 526 mm and subsequently to 549 mm on a tongue rail. So, stock rail and tongue rail accordingly the values have been given. So, there is a bit of a difference here. Similarly, when you talk about 1 in 8.5 fan shaped turnout, so here this ML is basically main line. So, on the main line side, here at joint it is 268 and then we have a uniform value of 600 mm up to the third sleeper, then it changes to 685, 620, 660 and then from 6 to 13 sleeper it remains as 600 mm. So, depending on the conditions, depending on the way it has been provided, these turnouts which will be having two types of the rails, tongue rail and a stock rail, and these we will be discussing when we discuss about the turnouts. These spacings are being provided. Now, in the case of this 1 in 8.5 fan shaped turnout, few other things are there, because in the previous one we said up to 13 sleeper it is 600, but now if we are going beyond 13 sleeper on the stock rail it remains 600 mm, between 13 and 14 on the tongue rail it changes, then again 14, 15 also it changes, and then 15 to 18th it becomes 598 mm. So, and these last two sequences keep repeating further. So, that is the overall arrangement in which the sleepers are being provided in the case of the turnouts. Now, the last thing which we are going to talk about the tolerances. So, the tolerances here are the sleeper to sleeper spacing on a normal track shall be within plus minus 20 mm. So, if we talk about 600 mm, we talk about 650 mm, or we said we are talking about less than that or more than that at joints they are 200, 150 etc. So, this is a tolerance. And sleeper to sleeper variation of a gauge on a normal track, that is 2 mm. So, these are the two tolerances related to the sleeper spacings are being defined, and I have informed you the same. So, with this we close today's discussion. We discussed the functions and the requirements of the sleepers which are being used on the tracks, the sleeper density, the sleeper spacing, and then finally towards the end we talked about the tolerances. With this we close this lecture. Thank you, and we will be meeting in the next lecture.